One of the key tools in calculus is integrals in addition to derivatives, and by all means integrals is the opposite approach to a derivative. In other words, it sort of removes the operation that was done by a derivative. But from an application standpoint, integrals are closely related to areas, specifically speaking, area under the curve. Now, the motivation behind integrals comes directly back to the area problem. So I'm going to start with the area problem. So what is the area problem? Well, we want to find the area under the curve. We can either call it a curve or a function. So I'm going to start with something very fundamental. Let's say we want to find area under the curve f of x is equal to 2 on the interval 0 to 2. I'm going to draw the function. So f of x is equal to 2 is simply y equals 2. So that is the function between 0 and 2. Now, we want to find the area under that curve. It should be quite obvious now just by looking at it. So the area would be all of that. And the shape of it, naturally, it is a rectangle. So we can readily find the area of this particular rectangle. The height here is 2. The length here is 2. So the area is simply 2 times 2, which would give us 4. Very easy. Now, is there a different way to approach this problem? So there is a reason why I'm doing it this way. So what I'm going to do is I'm going to chop the area into 4 pieces from the left hand side. So 1, 2, 3, 4. And I am going to do 1/2, 1, 3/2, and 2. So now I end up having 4 different rectangles. So I'll call this rectangle or area 1, area 2, area 3, and area 4. So now I would end up having 4 different areas. And if I want to find the total area under the curve, the area under the curve would simply be equal to A1 plus A2 plus A3 plus A4. Now, it may seem silly that, that we're splitting it up into 4 rectangles and trying to find the area which we know is 4 already. But the reason I'm doing this is to illustrate a point on how we can extend this to more complex functions. So how do we find the area of each of these rectangles? So A1 is simply the height, which is 2. But the width in this case, though, is 1/2 for each rectangle. So the first rectangle would be 1/2 times 2. The second rectangle, which would give us 1. The second rectangle is identical to the first. The third rectangle. And the fourth rectangle. And we eventually add all of them together. Is simply 4. Now, what I'm trying to illustrate here is the area under the curve can be approximated by using a bunch of rectangles. Now, and summing the areas of those rectangles. In other words, we are trying to do an approximation of the area under the curve. So let's take a curve of that sort. Clearly, that is not going to be as straightforward as the rectangle case that we had previously. Now, we'll just say that is some function, and we want to find the area under this curve. In other words, we are trying to find the area over there. And how do we get that area? We know the value of the function is defined by the curve. So that would be f of x. And we want to come up with the area between 0 and 2. There are a couple of ways to do this. We could either start from the right endpoint and go to the function, or we can go to the left endpoint. So it's just a matter of choice. Now I'm going to show you both. First, I'm going to define the function properly as a parabola. So I'll just call that f of x is equal to x squared. And I'm going to start at 0 and go all the way up to 2. So that would be 4. I'm going to have, let's just say we will use 4 endpoints like we did in the previous case. So 1/2, 1, 3/2, and 2. Now, I could pick the left endpoints, which are right over here, and go toward the right side, and I can actually get the rectangles, and I would have 3 rectangles, and this is what we call the left sum when I write the sums of the rectangles. So that's my first rectangle, my second rectangle, and the third one. And I'll call this to be A1, A2, and A3. So I want to find the area under the curve, which would be the sum of A1, A2, and A3. So A1 plus A2 plus A3. Now, in the previous problem, the rectangles were identical. In this problem, though, the rectangles are not identical. The heights differ. We have different heights. So the areas are going to be different. So since we started at the left endpoint, the height over here and the height over there and the height over there can be obtained by evaluating the function at those points. So in other words, f of 1/2, f of 1, and f of 2. That's simply 1/2 squared. F of 1 is 1 squared, which is 1. F of 3 over 2 would be equal to 9 over 4. So if I add them all together, I have 1 over 4 plus 1 plus 9 over 4. I have 10 over 4 plus 1, 14 over 4, which would give us 7 over 2. Now, that is one area, and that's what we call the left area. We'll call it the left sum. Now, the other area is obtained by evaluating the right sum. Oh. Trying to get this graph as close as possible to the previous one. Perhaps that is good enough. It is the same function. So that would be f of x equals x squared. And 0 to 2, x and y. And we are going to evaluate the right sum now. I'm going to pick the endpoints like we did above. So 1/2, 1, and 3 over 2. Only this time, instead of starting on the left-hand side, I am rather going to pick the right-hand side. So by right-hand side, I mean the right endpoints. So the rectangles that I am planning to have are okay. So let me draw the rectangle. So those are the 4 rectangles. So clearly the rectangles go outside of the curve. So now the area of each of those rectangles would be those. And we know those points correspond to the function. So we know the y values. The y there is f of 1 over 2, which is 1 over 4. Over there, it's f of 1. We get 1. Over there, it's f of 3 over 2. We get 9 over 4. And f of 2 would be 2 squared. You get 4. Now, the area under the curve in this case, the right sum, because we start from the right-hand side, is A1 plus A2 plus A3 plus A4. So that would be A4, A3, A2, and A1. So the first rectangle has a height of 1, 4. The width is 1/2. So we get 1 over 8. I believe I forgot to do something in the previous problem. I simply put the width, but I forgot to multiply it by 1/2. Apologies. So you have to multiply by 1/2. So times 1/2 times 1/2 times 1/2. You get 7 over 4. So now A2 would be the width is 1/2. The height for the second rectangle is 1. So we get 1/2. A3, the width is still 1/2. The height is 9 over 4. Which would give us 9 over 8. A4 is 1/2 multiplied by the height, which is 4, which would give us 2. So the area in this case would be 1/8 plus 1/2 plus 9 over 8 plus 2. Which would give us 10 over 8 plus 1/2 plus 2. I could combine those 14, 16 divided by 8, which would be 30 divided by 8. (15 over 4). So what we have is the area from the right-hand side, the right sum, and the left sum. Clearly, you can see we're trying to find the area under the curve, but with the right sum, we are actually overestimating because the rectangles that we formed go outside of the curve. With the left sum, we are underestimating the area. So the concept here is, as we move on and when I formalize this, things would become obvious, but the concept here is the true area will be between the left and the right sums. And that is a given. So what do I mean when I say that the true area under the curve will be between the left and right sums? That goes back to an overestimate and an underestimate. If something is overestimated, underestimated, the true estimate has to be between the overestimated value and the underestimated value. That said, instead of arbitrarily picking the number of rectangles, these are called approximating rectangles, we can divide the interval into n plus 1 endpoints, or sample points. We'll call this sample points. Now I'll draw this in the graph and I'll demonstrate it in a bit. And we can formally define the left and the right sums. So the width delta x is simply the upper minus the lower divided by the number of sample points that we need. And x naught would be the starting point plus delta x. X1 would be starting point 2 times delta x. X2 would be starting point 3 times delta x, and so forth. So if we define it in this way, we can go back to our previous problem, relate to previous problem. So A would be 0, B was 2, and if you look at the graph, we simply had 1, 2, 3, 4 sample points in both cases. And the sample points were at 1/2, 1, 3/2, and 2. So you can see the number of sample points were 4. Was 4. So delta x would simply be 2 minus 0 divided by 4, which would give us 1/2. If I plug those values in, I would have the first sample point as the starting point, which is 0, plus 1/2, which would give us 1/2. So the next one would be starting point plus 2 times 1/2, which would give us 1. The next starting point would be 0. Next sample point would be starting point 3 times 1/2, 3/2. And the last one would be 0 plus 4 times 1/2, which would give us 2. And you can see these 4 values match up to the sample points that we have here. And over there. Now we just have to formalize how we write the left and the right sum in this case. So now we could relate the left sum and the right sum to the sample points that I wrote. So if you look at the graph, the left sum used the points 1/2, 1, and 3/2. So the left sum uses x0, x1, and x2. The right sum uses the right sum uses x1, x2, and x3 as sample points. Now, what we did is we found the area, and the area was evaluated by finding the height and multiplying it by the width. Now the width in our case is fixed, and we fix it as delta x. The height, we used the function to evaluate it. So for the left sum, I could simply write it as, going to formalize it, I'll call it L4. That 4 indicates the number of sample points that we have, 4 sample points. So x1 and x2 multiplied by delta x, because I multiplied by the width over there, which is 1/2, the one that I forgot to do at the very beginning. So that's how I would evaluate the left sum. The right sum in this case would be f1, or f of 1, f of x2, and f of x3 multiplied by delta x. So for arbitrary n, the left and right sum and the right sum would simply be f of x1 plus f of x2 all the way up to f of x n minus 1. That should probably be n minus 2. Okay, now we could use the summation notation to write this in a different way. Or we could change the indices, and instead of writing that as n minus 2, we can move the indices and call that as n, and that as n minus 1. And the left sum summation from I 0 to n minus 1, I from 0 to n minus 1, sum over all values f of xi times delta x. And the right sum is sum I equals 1 to n f of xi times delta x. Now, what do you think would happen if we increased the number of sample points? The more sample points we have, the more rectangles we're going to have. So more sample points implies more approximating rectangles. And that is going to give the better estimate for the area. So if we had infinitely many rectangles, what we say is the limit n approaches infinity of the left sum, limit n approaches infinity of the right sum would approach a and A is the true area under the curve. That is, if we use infinitely many approximating rectangles, we will get the actual area under the curve. So the more sample points we have, the more rectangles we are going to get, and eventually we will capture the true area. So when I do a problem, I'll do two different cases, and you can see how things would change. So here is a function. What we have is f of x is equal to 1 over x. And we start at 1 and we go all the way up to 2. First, we've got to graph set the window from 1 to 2, and the y values, it's probably going to decrease toward 0.5, so 1 to 0.4, and graph, 2. Have the order reversed. So that is our curve. So something like that. So that point right there is 1, and that point is 2. That is our curve, f of x equals 1 over x. And we need 4 approximating rectangles. In other words, we need to have 1, 2, 3, 1, 2, 3, 4. So we need to have 4 endpoints. So we have to divide 2 minus 1 divided by 4, get 1 over 4. So 1 plus 1 over 4, it's 5 over 4, plus 1 over 4, 3 over 2, plus 1 over 4, 7 over 4, and lastly we have 2. So we have to use the left endpoint, which would simply mean I am going to use, or is it the right endpoint? So we have to use the right endpoints. So and those are the right endpoints, and we could find the values here, which would give us the height. So 1 over 5 over 4 is 4 over 5. There, it's 2 over 3. 7 over 4, I'm plugging it in the function. So 1 over 7 over 4 is 4 over 7. And lastly, I have 2. So the right endpoint here is going to give us an underestimate because the function is decreasing. If the function were to be increasing, it would give us an overestimate. So since the function is decreasing, the right endpoints would result in an underestimate because the rectangles leave us with some gaps. So there is a gap here that's unaccounted for, gap there, gap there, gap there. So that has to be the lower endpoint. I evaluated the function at each of the endpoints here, there, there, and there. So I would simply have 5 over 4 times 4 over 5, 3 over 2 times, 4 over 5 plus 2 over 3 plus 4 over 7 plus 2 multiplied by delta x, which is 1 over 4. If I combine those two, I would simply have 10, 12, 22 over 15, and 4 over 7 plus 2 multiplied by 1 over 4. 154 over 105 plus 60 over 105 plus 210 divided by 105. I'm getting a common denominator here. One 54, 60, 214. Add 210 to that. We have 424 divided by 105 times 4, which is 106 over 105. And that is the final answer. Now we can move on to finding the right sum. So we'll add a page here. So the right sum needs a graph, a similar graph. We have a function of that form. We have our endpoints, or sample points, not endpoints. And this time, I have to evaluate that value is going to be 1. And that value is going to be 4 over 5. And that is going to be 2 over 3. That is going to be 4 over 7. And that is all. Now we have to construct the rectangles. So the first rectangle is going to be that. The second rectangle would be that. The third would be that. And the fourth would be that. So I'm going to go ahead and use a different color for the rectangles. And you can see we are going to overestimate the area because the rectangles exceed the curve, and it happens in this case, and it is in direct contrast to what we did here, because the function is increasing in that example and it is decreasing in this example. So R4 would simply be equal to one, which is the height of the rectangle, the height of the next rectangle, height of the next rectangle, and multiplied by 1/4, which is the width. So if we add everything together, we have 15/15, 12/15, 10/15, plus 60/15, actually 1/5. So if we combine those terms, we have 25, 35, 37 divided by 15. We need to have a common denominator. So I'm going to multiply and divide by 7. So I'll have 9, 259/1/5, plus 60/1/5, multiplied by 1/4. So 259 plus 60 is 9, 11, 319/1/5. Get 1/4. That gives a value of 0.7595. I forgot to include that point over there. So that's the excess area. Feels like I made a mistake somewhere, because that area seems to be higher than this. So that is going to be an overestimate. So I'll call that as R4, and this would be L4. And it reverses here because the function is decreasing. So we've got to be careful, and oftentimes still something doesn't add up. Aha! So now we can move on to finding the right sum. sort out a page here. So the right sum needs a graph, a similar graph. We have a function of that form. We have our endpoints, or sample points, not endpoints. And this time, I have to evaluate that value is going to be 1. And that value is going to be 4 over 5. And that is going to be 2 over 3. That is going to be 4 over 7. And that is all. Now we have to construct the rectangles. So the first rectangle is going to be that. The second rectangle would be that. The third would be that. And the fourth would be that. So I'm going to go ahead and use a different color for the rectangles. And you can see we are going to overestimate the area because the rectangles exceed the curve. And it happens in this case, and it is in direct contrast to what we did here, because the function is increasing in that example, and it is decreasing in this example. So R4 can be found easily using a similar approach. Let me delete this. But before I go to that step, I believe that has to be 1/2. So of course, we could use a calculator to evaluate it. Let's just do that. A bit easier instead of dealing with fractions. So 154 over 105 plus 60 over 105 plus 1/2 divided by 4, we end up getting 0.6345. Now, the R4 part, the right sum, we have the height. Clearly, we have extra amounts here, so this is going to be an overestimate. Again, this is slightly different from the previous problem because that is an increasing function. This is a decreasing function, so things would just flip, and you've got to be careful in determining the right sum and the left sum. And if it's an overestimate or an underestimate, so we have the first height, that's 1. The second height is 4 over 5. Third is 2 over 3. The fourth is 4 over 7. And I multiply by delta x, which is 1 over 4. So we have 1 plus 4 over 5 plus 2 over 3 plus 4 over 7 multiplied or divided by 4, we get 0.7595. So clearly L4, R4, the true area. L4 happens to be 0.6345, and that happens to be 0.7595. And I know the actual area for this. We will talk about this later. So the true area is 0.6931, and you can see that clearly lies between the lower sum and the upper sum. So this true area is given to you. Here is another example of estimating areas using rectangles. This is a slightly different problem where we're going to use 3 rectangles first, then we're going to increase it to 6 rectangles. The point of the example is to recognize that as we increase the number of endpoints, the estimate is going to be more accurate. Now, we're going to take 3 different approaches, one using left endpoints, the other using right endpoints, and midpoints. Now, another thing to realize here, not only are we going to get a better approximation by increasing the number of rectangles, we could also see a change in the left and right endpoint interpretation, because this particular function has increasing behavior. So I can graph it first. Going to set it from -1 to 2 because that is the range or the domain of values where the function is defined, and the value of y is not going to exceed 5, so I'm going to set it at 5. And that is the graph that we get. When x is 0, we're going to be at 1. Should have done it in one stroke, would have been better, but I'm going to try this time to get it right. That's good enough. Copy this for later. And later we could paste this so that we have the same graph. So what we have here is -1, and over there it is 2. And the function in question, f of x, is 1 plus x squared. Now, we want to use 3 rectangles first. which would imply delta x is equal to b minus a divided by 3. So we have 2 minus of minus 1 divided by 3. 3 over 3, we get 1. So we are going to move from negative 1 to 0, 0 to 1, and 1 to 2. So we can see that delta x here would be 1. Same there. And there. Now that we have the rectangles, I'm going to start by using right endpoints. So let's start with right endpoints. So that would be my first rectangle. And you can see that the first rectangle is going to result in an overestimate. The second rectangle would also result in an overestimate, whereas the third rectangle would result in an underestimate. Now you've got to keep in mind this happens because on one side the function is decreasing, the other side the function is increasing. So that is why we are getting overestimates on one side, underestimates on the other side. So my rectangles end up being 1, 2, and 3. I'll call that A1, A2, and A3. So the area under the curve, or under the graph, is simply A1 plus A2 plus A3. So how do we find the area? We've got to identify the heights of each of those rectangles. So to do that, we need to know those points over there, and over there. That'll give us the height. How do we find those points? We simply plug in the x values, find the corresponding y, and we'd know the height. So f of 2 would be 1 plus 2 squared, and we would get 5 right there. F of 1 would be equal to 1 plus 1 squared, we'd get 2. And here, f of 0, and we'd get y equals 1. So the height at x is equal to 0 is 1, height at x is equal to 1 is 2, and the height at x is equal to 2 is 5. So the area of the first rectangle is length 1, height 1, you get 1. The second rectangle, length is 1, height is 2. The third rectangle, length is 1, height is 5. I'll call this the right sum, so R3, because we have 3 endpoints, and that would equal to 1 plus 2 plus 5, which is 7, plus 1, we get 8. So now we are going to move on and use the same trick. 3 endpoints, but only this time we're going to start from the left hand side. So if I start at the left endpoint, that would be my first rectangle. That would be my second rectangle. And that would be my third rectangle. So those would be the areas. I have A1, A2, and A3. Those points are y equals 1 plus 1 squared, which would be 2. At that point, we know that y is 1. And over there, we know that y is 2. So the area under the graph is A equals A1 plus A2 plus A3. And A1 would simply be equal to one times 2. 2 would be the height over there, which is 2. A2 would be equal to 1 times 1. We'll get 1. And A3 would be 1 times 2. We'll get 2. So I'll call this L3 because we are looking at the left endpoints. So we'd have 2 plus 1 plus 2. You get 5. And there we have another case using midpoints. Now, what do we mean by midpoints? We have to find the central point between 0 and 1, 1 and 2, and so forth. So again, we have the function x, y, and f of x is equal to 1 plus x squared. Now, the sample points that we have are 0, 1, and 2, and -1. So we have to look at the midpoint. What is the midpoint between 0 and -1? Which is right over there. And we will get -0.5. The midpoint between 0 and 1 is 0.5. The midpoint between 1 and 2 is 1.5, or 3 over 2. So now my rectangles should be constructed in this manner. So the area that we would have, so that's rectangle 1. Now, the rectangle here are symmetric, so I'm just going to go for a symmetric case. That'll be rectangle 2. And finally rectangle 3. and right over there. So perhaps to avoid confusion, draw it this way. So that would be our first rectangle, second rectangle, and the third rectangle. So the first rectangle, so I'll call this M3 because we are using 3 as sample points. So M3 is once again A1, A2, A3, and the sum of those. So A1 would equal to the width of the first rectangle. In this case, it is -1 or units. It has to be positive, so 1. What is the height? The height here is 1. So 1 times 1, we get 1. A2 is 1 times 1 also, we get 1. And A3, the width is 1. And the height in this case, excuse me, it can't be 1. I take that back. So at the midpoint, right here, we have 0.5 and 0.5, and that's a midpoint, 1.5. So we've got to evaluate these values. So at the midpoint, y would be equal to 1 plus minus 0.5 squared. That would be 1 plus 1 over 4. We get 5 over 4. There, it is 1 plus 0.5 squared. Still be 5 over 4. And that point, we would have y equals 1 plus 1.5 squared. Be 13 over 4. So A1 would simply be equal, so that is not 1, I take that back. It would be 5 over 4 multiplied by the width of that first rectangle, which is 1, so we get 5 over 4. A2 is also 5 over 4. Height, width is 1, we have 5 over 4. A3 would be, the height is 13 over 4 multiplied by the width, you get 1. So we have 13 over 4. If I add all of those, I'd get 23 divided by 4. And you can see the estimate that we got for R3 is 8, L3 is 5, M3 is 23 over 4. That has to be close to 5 point something. So let's just evaluate in the calculator. We have 5.75. So what did we see here? Based on M3, L3 and R3, L3 gives us an area of 5. M3 gave us an area of 5.75. R3 gave us an area of 8. So clearly M3 is between L3 and R3. That's what we would expect because M3 is based on the midpoint. L3 is left endpoint based. And R3 is the right endpoint based calculation. Oops, 8/3 minus 7/3 plus 1. Okay. Now let's increase it to 6 rectangles. So first we've got to find delta x. Delta x would be b minus a divided by 6, I'm sorry. We have 6 endpoints now. So 2 minus of minus 1 divided by 6. And you should have 3/6, which would give us 1/2. You've got to ask yourself, are we going to get a better estimate of the area, or are we going to get a worse estimate of the area? We are increasing the number of rectangles, so the estimate of the area is going to be better. So those are my endpoint values. Now I'd like to go from negative 1/2 to 2, negative 1 to 2, in increments of half. So I'd have negative 1/2, 0, 1/2, 1, and 3/2, which is 1.5. So those are the rectangles that I would have. So let's start by going from the left. Or did we do right first? We did right first. So let's start on the right hand side. So that's my right endpoint. So the area corresponding to that will be all of that. Right endpoint ends there. The area will be right there. Next rectangle. Next rectangle. And at 0, I would have over there. Next rectangle. And at 1/2, I'll have that point. And that would be the rectangle. So we have rectangle 1, 2, 3, 4, 5, and 6. So I'll call this A1, A2, A3, A4, A5, A6. So let's find L6. I'm using the right endpoints, using 6 sample points, hence I'm going to put it as R6, and that would be the sum of A1, A2, A3, A4, A5, and A6. We already know some of the endpoints here. At y equals 2, we have 5. So the value of y here is 5. The value of y there is 1 plus 9 over 4, which is 13 over 4. The value of y here is 1 plus 1, we get 2. The value of y here is 5 over 4. The value of y there is 5 over 4. And that's all we would have. So A1 is the width, 1/2, times the height, 5 over 4 for the first rectangle. We get 5 over 8. A2 is the height of that rectangle over there, which is at 1. So we have 1/2 times 1, which should be 1/2. A3 is 1/2 times 5 over 4, which is 5 over 8. A4 is 1/2 times 2, which, because 2 is right over there. We get 1, should be 1. A5 would be 1/2 times 13 over 4, which would give us 13 over 8. A6 is 1/2 times 5, we get 5 over 2. Now we just have to add all these. R6 would be 5 over 8, plus 1/2, which I could write it as 4 over 8, plus 5 over 8, plus 8 over 8 for 1, 13 over 8, plus 5 over 8. I just wanted to have a common denominator, so I have 8 and 5 plus 4, 9, 14, 22, 35, and 40. I end up getting 5. Okay. We are going to move on to the left sum. So same process. Endpoints. Y is 1 plus x squared. -1, 2, -1/2, 0, 1/2, 1, 3 over 2. So I've marked all the endpoints. Now I just have to draw the rectangles from the left-hand side. So I'm going to start with my rectangle from the left-hand side. So it's going to go up there and drop down. The next point is right over here. So it's going to go up to that point and drop down. At 0, we are at 1. So I'm going to go that way and drop down. At 1/2, we are there. So I have to go that way and drop down. And the next point is over there, right, and down. The next point is over there, right, and down. So the points that we are going to use would be the first endpoint, -1. Here y is equal to 2. The next point, we know that value already. That was y equals 5 over 4. We know that point is y equals 1. And that would be y equals 5 over 4 also. Right there, it's y equals 2. And right there, it's y equals 13 over 4. And that would give us A1, A2, A3, A4, A5, and A6. L6 would be equal to A1 plus A2 plus A3 plus A4 plus A5 plus A6. A1 is the area of the first rectangle, width is 1/2, height is 2, so we get 1. A2 is the length of the second rectangle, which is 1/2 multiplied by its height, 5 over 4, we get 5 over 8. A3 is 1/2 multiplied by 1, we get 1/2. A4, we have 1/2 multiplied by the height, which is 5 over 4, we get 5 over 8. A5, we have 1/2 as the width, and the height is 2. And A6 is 1/2 the width multiplied by 13 over 4. L6 will then be the sum of those values, so we have 1, which is 8 over 8, plus 5 over 8, plus 4 over 8, plus 5 over 8, plus 8 over 8, plus 13 over 8. If we add them all together, we have 10, 14, 22, 30, 43 over 8. That's odd. It looks like the left sum seems to be greater than the right sum, which means I made a mistake somewhere in finding the right sum. Let's see. A1 is 5 over 8, A2 is 1/2, 4 over 8, A3 is 5 over 8, A4, 8 over 8, 13 over 8. 5 times 4 over 2 times 4. It's not simply 5 over 8, rather it is 20 over 8. So the answer is 55 over 8. Now everything looks okay. Great. So that shouldn't change. Oh my. Did we do this right over here? I think we didn't make a mistake here. Everything is in place. So now we have 43 over 8, which we shall evaluate that. That's about 5.375. Let's see where these points fall. Now, using midpoints, we still have to do midpoints. We have 6 rectangles, so we've got to evaluate midpoints of those 6 rectangles and use the midpoints to identify the area. So let's finish that first, and we could come back and compare the areas. So first endpoint, second endpoint, -1, 2, x, y. And the points that we have are -1/2, 0, 1/2, 1, and 3/2. So how do we draw these rectangles? Well, we start at that point, we go toward either side and connect. First rectangle, start at that point, go toward either side, area of that rectangle, start at that point, go toward either side, we'll get that rectangle, and start at that side. We can't go either side, so we'll just fill that in over there. Should we include that though? We shouldn't. We'll simply keep those, and we know each of the did I go either side? I didn't, so I have to come over there. Okay, so now the rectangles that I have, since I'm using midpoints, first one would be over here, the second one would be over there, the third one should be that. So call it A1, A2, A3. So based on the midpoint, the areas are A1 plus A2 plus A3. A1 is the height at -1/2, which we know is 5/4 times 1/2. Y there is 5/4. Same value, so 5/4. A2 is 5/4 times 1/2, which is right there, and that is 13/4. So A3 would be 13/4 times 1/2, which would give us 13/8. That is 5/8, 5/8, and when I add all of those together, 23/8. I get 2.875. And the right sum here reduces to 6.875. Let's put all the values. Let's start with L3. L3 was 5. L6 was 5.375. And M6 or M3 is 5.75. R3 was 8. M6 looks like I made a mistake in M6. The width. Bad mistake there. The width is not 1/2. If you look at the rectangles, the width over here is 1. Width over there is 1. Width over there is 1. So sometimes you just have to think about items twice and you can catch mistakes. So that gives me 23/4. It's 5.75. So M6 happens to be the same value, and R6 is 6.875. So when we use 3 rectangles, our guess estimated area lies between 5 and 8 with n equals 3. The estimated area lies between 5.375 and 6.875 with n equals 6. And if we keep on going, and as we increase n, what do we expect to happen? The interval will start narrowing toward the actual area. So if n approaches infinity, eventually it's going to squeeze further and further and further and get to the exact value of the area. And that is what we would expect to see. And I know because I know what integrals are based on the knowledge that I have about integrals. I know the actual area for this problem is 6. So as things get narrower and narrower, it is going to approach toward 6, and you will get the area to be 6. So the key idea here is if we increase the number of rectangles, the area that you estimate is going to become more and more accurate. So the distance problem is no different from the area problem. We're just going to interpret it in a different way. Recall, if you recall, distance or velocity is simply distance over time. But that perhaps is the definition in physics, but in reality, when we quantify velocity, we end up saying, okay, velocity is how distance changed with respect to a time change. So this is actually the change in distance divided by the change in time. So if you remember from derivatives, a change in distance, I could call it as delta t, divided by, delta d divided by the change in time, which is delta t. So if we want to find the distance, delta d is v times delta t. So now you can connect the dots between this approach here and the definitions that we used here for the left and right sum. You could see that I have f of x at specified points and delta x. So I'm going to use the same trick. So if v, velocity, happens to be a function of time, evaluated at, say, t1, t2, all the way up to tn, or start at t0, and i.e. f of t. So this would be f of t naught multiplied by delta t, f of t1 multiplied by delta t, f of t2 multiplied by delta t, all the way up to f of t n minus 1 multiplied by delta t. And that would be the lower estimate for distance. In the summation form, we could simply write it as sum I equals 0 to n minus 1 f of ti multiplied by delta t. And you can see this is very similar to what we had earlier for a function. In a similar manner, if we have Rn, we know Rn starts at 1, so delta t, t2 delta t, all the way up to f of tn delta t. And if you sum all of those values and put it in summation notation, f of ti delta t, and that would be the upper estimate for distance. So all we are trying to say is if the velocity function is known, the area under its graph is the distance. So you can see that the distance problem is also an example or a motivational example for integrals. So by finding the area under the curve for a velocity function, we are pretty much finding the distance. So here is an example. We have a table and I'm going to draw a graph. The time increments are 0, 0.5, 1, 1.5, 2, 2.5, and 3. X-axis values, we have 5, 10, 15, 20, 25. Now I'm just going to graph these. At 0.5 I have 6.2. At 10 I end up having, or at 1 I end up having 10.8. At 1.5 I have 14.9. At 2 I have 18.1. At 2.5 I have 19.4, which is very close. At 3 I have 20.2. Connect the dots. So let's go ahead and write these points. Let me redo this. At 0, we have 0. 0.5, we have 6.2. At 1, we have 10.8. At 1.5, we have 14.9. At 2, we have 18.1. At 2.5, we have close to 20, 19.1. And at 3, we have 20.2. And you can see that is the velocity function, f of t. Change that to t in seconds and velocity y. So that is the velocity function. Now if we find the area under this, we are going to find the distance. In the previous problems, we had a function and we had to evaluate the values of the function at each of the points that we have, the sample points, to find the velocity. But here, they've given us the points, so they made things easy for us. So let me go ahead and copy this, so we can reuse it later. So the points are 0.5 and 6.2, 1, 10.8, 1.5 and 14.9, 2, and 18.1, 2.5 and 19.4, and lastly we have 30 and 2.2. So I'll copy it now one more time. Okay, let's go ahead and copy. So they want us to find the lower and upper estimates for the distance. So let's start with the lower estimates. So these are our endpoints. For each rectangle, which would be our sample points. So since we are starting on the left-hand side, so I have my first rectangle going that way, second rectangle going that way, third, fourth, fifth, and clearly the lower sum is going to be an underestimate. So I have 5 rectangles. And I'm going to find the area under the curve, which would give us the distance estimate. lower sum or left sum. Left sum uses left endpoints. So that would be equal to area 1 plus area 2, area 3, area 4, and area 5. So add the areas. The width here, delta t, is simply 0.5. It's all 0.5 increments. So the area of the first rectangle, the height is 6.2 times 0.5. That's A1. A2 is the height of the second point, 10.8 times 0.5. A3 is 14.9 times 0.5. A4 is 18.1 times 0.5. And A5 is simply 19.4 times 0.5. If I add those values, let's make use of a calculator. Since we use 5 rectangles, 5 endpoints, I'm going to call it as L5. So 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4. Multiply all of those by 0.5, and the distance is 34.7. Now, if things moved in a linear fashion, we don't have to go through this, because if it's a linear fashion, then the slope of that line could easily give us the velocity, or relate the velocity to the distance and so forth. But it's not linear here, which is why we're taking this approach to find the distance traveled. So the distance traveled, the lower estimate, is simply 34.7 feet. So we have to do the same, but this time we're going to do it for the right estimate. So let's paste the graph here. Mark out our endpoints for each rectangle. And this time we're going to start from the right hand side. So let's sketch out the rectangles. So from there, going to go that way, down. Going to go that way, down, that way, down, that way, down, that way, down. Seems like we are going to have an overestimate this time. A1, A2, A3, A4, A5. So the distance using the right sum is R5 equals A1 plus A2 plus A3 plus A4 plus A5. A1 is 10.8 multiplied, because it is the height of, we'll start here. start with A5 and go down. So A1 is right there. So that height is 10.8. A2 is that height. It's 14.9 times 0.5. A3 is that height. 18.1 times 0.5. A4 is that height. 19.4 times 0.5. And lastly, A5 would be that height, 20.2 times 0.5. So R5 would simply be 10.8 plus 14.9 plus 18.1 plus 19.4 plus 20.2 times 0.5. And that gives us an estimate of 41.7 feet. So the distance traveled is between 34.7 feet and 41.7 feet. And that is how we find the distance when we don't have a linear relationship. Now, even though we have a curve, we were able to identify the distance using lower or left and right sums and the concept of approximating rectangles and finding the area under the velocity curve. Here is an example where the velocity graph of a car is given to us, and we want to estimate the distance traveled by the car when the brakes are applied. So at time 0, the brake was applied, and a few seconds later, at time t equals 6, the car came to a stop. And we want to see the distance traveled. The question here is, should we use the right sum or the left sum? Well, you look at the curve, the function is decreasing. Which would imply that the right sum will give us the lower endpoint. It's the lower limit. Of course, it's better to try both of them and see which is better, or get a good estimate, not which is better. So here we have the graph, and perhaps we can pick our endpoints at 5, 4, 3, 2, 1. And from the left we can, or from right, we could draw a line to form a rectangle. And that is going to give us our lower endpoint for the distance. Delta x here is 1. It's the same for all intervals. So the height at each point, that point perhaps is about 50. We'll call that 50. And that seems to be about 35, 22, or even 25. It's probably about 17. That is about 5. Of course, these are estimates anyways. So the lower sum, I'll call it L5 because we have 5 rectangles, 5 endpoints. So the height of the first rectangle is 50. Second is 35. Third is 25. Fourth is 17. And the last one is 5. So 50 plus 35 plus 25 plus 17 plus 5 multiplied by 1 because delta x is 1. And that is the width of each of those rectangles, and the width is the same. So we will simply have 85, 105, 120, 137 and 142 feet. We could use a similar strategy to find the right sum. Oh, I meant to say left sum, not right sum. So I'm going to start at the left endpoint and go over and down, over, down, over, down, over, down, over, down. And each of those points, right there, it's probably about 70. We have that to be 50, 35, 25, 17, 5 and 0. We have 5 rectangles, so R5. Length times width. The width is just 1 in this problem, so we could simply do 70 plus 50 plus 35 plus 25 plus 17. That would give us 120, 155, 160, 180 and 197 feet, and 85 and 10, 127, 132. That's not 142. So the distance traveled is between 132 feet and 197 feet. So even though this is a nice little process, we don't want to draw rectangles each and every time and go through this tedious process to find an answer. So slowly, as we move into the definite integral, this area under the curve can be estimated accurately by using integrals instead of approximating using rectangles, because we already have this particular relation here which explains the left and right sum in terms of limits. Limits simply suggests that as n approaches infinity, then we can get the true value of the area under the curve. In other words, you need to have infinitely many approximation rectangles to get to the actual area. But that is not realistic. We can't do this for more than, say, 20 rectangles under the curve. And that is where an integral comes into play. And there are standard integrals, and we can simply integrate it and find the answer to any problem right away.